Share so it gets in the recording. Give you just 1 more minute. Stop share. Afternoon. Still got to get an answer in. All right. I'll look answers here in 15 seconds. All right, locking answers here in 5, 4, 3, 2, and 1. So what's the answer? Everyone should know it, especially after Wednesday. Yep, 2 divided by s squared plus 4. So was the correction we had to make, right? Laplace transform of sine of 2t. Uh-oh. 2 divided by s squared plus 2 squared. But 2 squared is 4. So, any questions? And shrink my head a little bit. All right, so one of the perceived benefits of this Laplace transform, it still can't really handle anything other than, or easily handle anything other than second order linear differential equations with constant coefficients, but it can also handle higher order differential equations and also non-homogeneous differential equations with relative ease compared to something like variation of parameters. And it works better with initial value problems because it naturally incorporates what? Yeah, your initial conditions. Yep. So it naturally incorporates your initial conditions when you're trying to find this Laplace transform, so which is another reason why we prefer to use it. So we started with this problem. The fourth derivative of y minus y has got to be equal to 0. And we were given the 4 initial conditions that are needed for well-posedness of this initial value problem, that my function at 0 is 0, its first derivative is 1, second derivative is 0, and third derivative is 0. So when we did the Laplace transform of this, we found that the Laplace transform of my function or my solution y has got to be equal to, oh, it's really lagging. Come on. You don't get to see all the crazy green stuff that I'm drawing. Okay, now it's catching up. Well, at least it's up there. Laplace transform of y is equal to s squared divided by s to the fourth minus 1. All right, looks like you got all my green stuff. So, yay, not a bad response time now. So then our goal was to start breaking this thing up to where it looked like some of those Laplace transformations that we saw in our textbook, right? Because again, it just comes down to at this point recognizing the actual inverse Laplace transformation is a complicated thing, but we know what some expected outcomes are, and we know what a lot of our solutions are looking like after exposure and experience with a lot of these differential equations. So I say, okay, well, can I look along here and say, are there any parts, any solutions that I can see appearing from s squared divided by s to the fourth minus 1? Well, s to the fourth minus 1 gives me a power of s to the fourth, and that really would only work if maybe I was dealing with something in here, so I could maybe make this work. But it would need to be s minus the number 2 fourth power, which is not what we have. We said we had a bunch of squares, so we took that s to the fourth minus 1 and factored it into s squared plus 1 times s squared minus 1 in the denominator. But now I still have this s squared up in the numerator. So I go back and look and say, do any of these deal with what I'm looking for? Well, an s squared plus 1 squared with an s in the numerator, well, maybe I can get this so I can get a cosine term to appear. S squared plus 1 squared over a number a, well, as long as I get a 1 in the numerator to appear, maybe it's a sine. So I probably maybe want to have that, but the only thing that I have that deals with subtraction is maybe this hyperbolic cosine. So maybe I want to leave it as that, or I can make another little clever observation. S squared minus 1, can I factor that down any further? Well, I can't factor out -1, but I'm talking about breaking that quadratic down even more. And I think I'll say it a couple times. S plus 1 times s minus 1. So really what I have is an s squared divided by s squared plus 1 times an s minus 1 and an s plus 1. And if I'm getting really familiar with my Laplace transforms, what I'm looking at, if I get a denominator of s minus 1 or s plus 1, those are going to be, as long as I have a constant of 1 up in the numerator, going to be the outcomes from those exponential functions. But I don't want it written out like this, because I'm multiplying each of those terms in the denominator. What am I going to do to break up this fraction? Partial fraction decomposition. So we want to break up this entire fraction into something divided by s squared plus 1 times something divided by s minus 1 plus something divided by s plus 1. Now, what is going to go in that first numerator above s squared plus 1? So it's an unknown polynomial. Really? Really? What was the boo-boo of mine that we had to correct on Wednesday? If it's a second degree polynomial in the denominator, then the numerator, it has to be what degree? First degree, which means it's linear, which means this is going to have to be some number times s plus another number. Now, what that a and b are, I don't know. I'm going to have to figure it out, but this is what the form is going to be. Potentially a can be 0, potentially b could be 0. I don't know. But then I go to my s minus 1 term. What is its degree? First, which means in the numerator, I need to have a what degree polynomial? A 0 degree polynomial, which is just a constant function. So I get just another constant. And then similarly for s plus 1. So what we need is for that s squared over s squared plus 1 times s minus 1 times s plus 1 to be broken up into this system of this system of fractions. So I'm going to have 4 equations with 4 unknowns. So I'm going to get, after I multiply by the common denominator, as plus b times s minus 1 times s plus 1 plus a c times s squared plus 1 s minus 1 plus a d times s squared plus 1. Wait, no, that's a plus 1, and then this is a minus 1. So now I need to break this down. Again, it becomes an algebraic problem. Not necessarily an easy algebraic problem, but at least an algebraic problem. If I look at s minus 1 times s plus 1, what is that going to become? S minus 1 times s plus 1. S squared minus 1. And I'm doing that because I know I'm going to need to FOIL between my as plus b term and this term right here. And that's just going to make it a little bit easier to do. I'm going to take my c term and I'm going to go ahead and FOIL out that s squared plus 1 times s plus 1. What is that going to become? Take s, multiply it by an s squared plus 1, I get s cubed plus s squared. Take a 1, multiply it by an s squared plus 1. Or I said s squared, s cubed plus s. Taking 1 multiplied by an s squared plus 1, I get an s squared plus 1. Similar-ish happening for s squared plus 1 times s minus 1. But instead, it will become what? Yeah, so I'll get some minus terms in there. And then I finally go ahead and FOIL out that first term, or that first product, the as plus b times s squared plus 1. And get as cubed minus as plus bs squared minus b, and then also go ahead and distribute that c terms through. Oh. I was like, no, I did this multiplication correctly. What are you talking about? Yeah. So then a cs cubed plus cs squared plus cs plus 1 Well, that was a 1 times c. I just wrote the c backwards. Plus ds cubed minus ds squared plus ds minus 1 with a d written backwards. No, I'm kidding. Just minus d. And then I group together my s cubed terms, my s squared terms, my s terms, and my non-terms. So if I factor out s cubed, well, what terms have an s cubed to them? D. I'm going to factor out an s squared. What terms have an s squared? So I'll have a b plus c and a minus d. And then what terms just have an s? So it'd be a negative a, but yes, plus c plus d. And then I'll be subtracting b oh yeah, why did it go away? Plus c minus d. So now I'm going to get 4 equations for unknowns. The coefficient for my SQ term has to be what? 0, because do I see an SQ term on the left-hand side? No. Just got an S squared. So I know A plus C plus D has got to be equal to 0. What about B plus C minus D? What does that got to be equal to? C minus D has got to be equal to 1. What about minus A plus C plus D? And then that minus B plus C minus D. So I have to solve this system of equations. Now, why do you think I wrote it in this weird-ish looking way? Keep everything organized, right? You got to figure out what A, B, C, and D are, and what did I do vertically? Lined up all the A's together, lined up all the B's together, lined up all the C's and D's. So visually, it's going to help me solve this a little bit. So if you remember your linear algebra, for those of you who've been able to take it, this turns into a matrix system. So I have all of my coefficients A, B, C, and D, and I got to be equal to all of these values. 0, 1, 0, 0. And I'm going to get a coefficient matrix. What will be the values of my coefficient matrix along the first row? 0, 1, 1. What about the second row? Third row? And last row. So normally, when the systems start getting this big, it turns into a linear system. We've got our linear algebra, we do our reduction, figure out what A, B, and C, and D needs to be. So if linear algebra is something you've taken before, you're more than welcome to start using that. After conversations with some of you in here, I know not everyone's had linear algebra before. but I can still solve equations in the same way that we've been doing it. Adding and subtracting multiples of equations to other ones. So I look at my equations. How can I use any of these four to start reducing down some of the variables? What would happen if I added the first equation to the second equation? Yeah, B would cancel each other out, but I'd be left with an A plus a B plus a 2C is equal to 1. So from two equations, I had 4 unknowns, and okay, maybe reduce it to 3, that might be helpful. But if I took that first equation, added it to the third equation, these would cancel each other out, leaving me with just C plus D has got to be equal to 1. 0. So I didn't do anything to the first equation. When I take the first equation and add it to the second equation, or sorry, I kept saying second, I mean third. So let that third equation become the first equation plus the third equation. That reduces it from 3 variables to 2. That's probably a good thing to do. Well, I can do that somewhere else, can't I? Where else? Second and last one. If I take the second equation and add it to the last equation, what am I going to get? That last equation now becomes what? Minus 2. C plus D is equal to 0. It's going to have a B plus C minus D is equal to 1. I now have a 2C plus 2D is equal to 0. And those B's are going to cancel out. So B plus a negative B gives me a 0. C plus C is a 2C. And negative D plus a negative D gives me a negative 2D. And a 1 plus 0 gives me 1. So now when I look at this, okay, I still have 4 equations for unknowns, but what do I now have buried inside of that? I have a system of 2 equations and 2 unknowns. 2C plus 2D has got to be equal to 0, and 2C minus 2D has got to be equal to 1. So we just highlight that. And work with that simpler 2 by 2 equation. And again, I get to see a nice little reduction of this equation. Because what happens if I take the first equation and add it to the second equation? I get a 2C plus 2D is equal to 0, but then I'm going to get a 2C has got to be equal to 1. Which then means C has got to be equal to what? All right, well, if C is equal to half, what does D have to be equal to? So I now know what C and D are. But hey, go back to that original set of 4 equations, 4 unknowns. Once I know C and D, what is the next variable that I also get? A, and also what? B. So C is equal to 1/2. D is equal to -1/2. Sorry if I know I'm saying your way. And I'm going to get A is equal to, yeah, so it'll be +1/2 plus -1/2 equal to 0. And I get B +1/2 minus -1/2 also has to be equal to 0. So it tells me A is equal to 0 and B is equal to what? A is equal to 0 and B is equal to -1. If you'd have done a row reduction with that system of equations, you'd have gotten all the same values for A, B, C, and I'll be back there in a second. So remember, we had the Laplace transform of my function y is equal to s² over s² plus 1 times s minus 1 times s plus 1. Confirming. So we just said we could break this up into the addition of 3 different fractions. S² plus 1 over something or under something plus something over s minus 1 plus another something over s plus 1. Originally, this was A times S plus B by C and by D. We said A is what? 0. B is -1, which means it'll just be broken down into 1 over s² plus 1. My C was 1/2, so this will be plus 1/2 divided by s minus 1, and then -1/2 over s plus 1. So how are we doing so far? Again, are any of these, is any of this work calculus here? No, it's algebraic. Again, part of the reason why we use Laplace transforms. Not necessarily simplifying the problem unless you just absolutely prefer algebra over calculus. But more often than not, people consider algebra an easier thing to do, a less complicated thing to do than some calculus. All right, so now I have those forms. I want to make sure I can recognize these as the outcome of some known Laplace transformations. So let's start with this s² plus 1 term. Right now I have a -1 in the numerator. If I wanted an s² plus 1 and I don't have a variable in that variable s in the numerator, then what I need to be working with is the sine function. And we're looking for s² plus a², and in the numerator is an a². So my a here in this case is supposed to be what? Well, what do I square to get 1? 1. So I have a 1 squared down here in the denominator, which means I really just need a what up here in the numerator? A 1. So what do I do with that negative? I can't square it, because algebraically that wouldn't be equivalent to the expression that we currently have. Just pull it out front, right? And it's just multiplication by a -1. I can rewrite that as just a -1 times 1 over s squared plus 1. And then I look at this, okay, I want something over s minus 1 and s plus 1. Whether it be s minus 1 or s plus 1, those are both the Laplace transform of what function? Yeah, it's exponential function. So, do I need, for the outcome for the Laplace transform of an exponential function, do I need any constant up there other than 1? No, which means there's 1/2 and -1/2. I want to pull out as a factor or as a multiplication, coefficient multiplication. And I have to remember it's minus whatever the value is too. This is going to be plus 1/2 times 1 over s minus 1 minus 1/2 times 1 over, well, I want to change that s plus 1 into s minus some number, so I can make sure it's clear that I'm viewing this as a Laplace outcome from the Laplace transform of an exponential function. Well, adding 1 is the same thing as subtracting 1. What was that? Adding 1 is the same thing as subtracting 1. 1. So I now have this as negative Laplace transform output for 1 over s squared plus 1 times 1/2 times the Laplace transform, which is 1 over s minus 1 minus 1/2, whoops, times the Laplace transform that became 1 over s minus -1. Which means this is negative times the Laplace transform of sine of what? That first fraction. Just t. Plus 1/2 times Laplace transform of what function? Minus 1/2 times the Laplace transform of what function? Okay. And this is a linear operator, which means I can bring all those coefficients inside and combine them all into one Laplace transform. This is Laplace transform of sine of t plus 1/2 e to the t minus 1/2 e to the negative t. So what was my solution to that fourth order initial value problem? This is where I get to check my lecture notes. I'm off by a factor of 2. At least according to this. But will that matter? No. Because it was a nice homogeneous equation. Would matter if it's not homogeneous. So, what questions do you have? All right. So just one little note. We'll do this in blue. So what I'm talking about is when we go back to that Laplace transform, with this right here. S squared plus 1 and S squared minus 1. And one of the things that we recognized on, or some of you recognized on Wednesday, was that I could have potentially just left that second denominator, the second part of that denominator, as an S squared minus 1. Because if I go look at this list of various functions in their Laplace transforms, does any of these at least deal with in the denominator S squared minus a number squared? Yeah, which one is it? Sine or cosine, right? So if I did just the constant up here, if I'm looking at S squared minus 1 squared, I want just a 1, or I want just an S. So I know maybe one of those two will work. So I can just do my partial fraction decomposition. And when you do so, I claim you'll get the following values for A, B, C, and D. Double check, so B times S squared, 1/2 S squared, they'll give me that. Yeah. So then this means what I'm looking at is 1/2 over S squared plus 1 plus initial conditions might matter. Did we do anything wrong with solving the system of equation? So we must have made a boo-boo with our system of equations. So I'll at least continue this before we go find it. If I do 1 over S squared minus 1, that is the Laplace transform of what? Hyperbolic what? So I have a 1 over s squared minus 1 sine. What is for the cosine, hyperbolic cosine, what is in the numerator for my Laplace transform? My variable s. I don't have that here. I just have a constant. Constant is 1. So B, hyperbolic cosine of t giving me that it's a Laplace transform of 1/2 sine of t plus 1/2 hyperbolic cosine of t, and that's why I'm like, yeah, we must have messed something up with that system of equations. Anyone happen to remember how I can rewrite? Whoops, I had even said sine and then I wrote cosine. I was doing great all the way up until just now. Now my subconscious is trying to think about something else. And I'm dropping the ball. But still, hyperbolic sine, I can rewrite as what minus what all over 2. Give you a hint. It's supposed to be the same solution, technically off by a little bit. Hyperbolic sine is defined as e to the t minus e to the negative t all divided by 2, which is telling me that my solution is 1/2 sine of t plus really 1/4 e to the t minus e to the 1/4 e to the negative t. So we got to go find out what we messed up in that system of equations. What I was trying to make here, though, is that you could go about it in 2 different ways. Both should get you to the same answer as long as you do your system of equations right. All right, so first thing we did was say, take equation 3, add equation 1 to it. So the A's should cancel each other out, giving me 2 C's, 2 D's, and a 0. One, 0, 1. 1 A, C, D, negative B, C. Okay, and then we added equation 4 to equation 2. Oh, I know what it is. You see it? Here to here. Should not be a 2C, it should be a 4C. Which means really my C should be what? And then my D has to be negative 1/4. But I still get my A, capital A has to be what? 0. I think, did I copy that wrong? B plus C minus D. Yeah, because that's got to be equal to, not 0. B plus C minus D, that second equation is not equal to 0. It's equal to what? To 1. So I have B plus a half has got to be equal to 1, which means B is equal to 1/2. And that's how we get the exact solution. That's what I get for not doing row reduction with the matrix. So while you finish correcting all of that, what questions do you got for me? So one of the great things about Laplace transform, it turns out, is not only does it take all of these calculus problems and turn them into algebraic problems, but it can also handle differential equations that are non-homogeneous, but more importantly, that non-homogeneous term can be discontinuous. So on Monday, we're going to define something called the step function. Because it turns out that you can take the Laplace transform of a step function and it has a very nice, easy outcome. So what I mean about something with discontinuous, if you're thinking about rocket thrust and you're thinking about what would it be, acceleration, right? You'd have a set amount of acceleration for a certain period of time, and then it would hit a new phase. And the acceleration doesn't just, it's technically going to change slightly gradually, but it's almost an instantaneous change. So technically, the acceleration go from down, go down. All right. Constant acceleration, you hit phase 2, your acceleration is going to change a little bit because you're farther away from Earth and you need to make sure you're in your orbit. And then you're going to travel along that for a little bit while, and then you're going to again drop. Okay. So instead of having to break up a differential equation like that into 3 different parts, where you go from T1 or T0 to T1, then T1 to T2, then T2 to T3, you can just sum that up into one discontinuous function where you have these little jump discontinuities and still set up the differential equation and be able to solve it. And the solution that you come up with will also be able to handle those discontinuities. So that's what we're going to start defining on Monday, and I'll probably take us through the end of the semester. We might have time because we have, 6 classes left? We get 2 next week, 5 or 3 the following week, 1 class. 6 days left. So we won't be doing the step functions for all 6 days, but we'll take up most of them. All right. always, if you got questions for me, feel free to stick around and ask them. Otherwise, hope you have a good weekend. Try to enjoy it if you can. See that to the bottom?